What if you were to learn that everything you observe, from the grandest galaxies and all of matter to the very flow of time, arose from a minor ripple in the vacuum? This audiobook delves into one of the most audacious concepts in contemporary cosmology, the proposition that the universe was born from absolute nothingness, set in motion by a spontaneous quantum occurrence. By examining the latest scientific theories, we will see how the microscopic turbulence of the void might just hold the blueprint for everything that we know. A quantum fluctuation can be envisioned as the subtle stirring of water on a lake's surface. While it may look placid, underneath there is a constant churn of unseen currents and gentle oscillations. In a similar way, within the immense emptiness of the universe, a space where nothing appears to be, infinitesimal bubbles of energy can materialize, possessing the power to give birth to particles. These events are so incredibly brief that they can flash into existence and disappear in an instant, like sparks dying in the darkness. This reality presents a profound question. How can such minuscule disturbances have any bearing on a structure as vast as the entire universe? The solution can be found in the initial moments immediately following the Big Bang, a time when our cosmos was in a state of unimaginable temperature and density. During this primordial phase, quantum fluctuations assumed a crucial role, planting the seeds of matter and energy that would ultimately grow into the galaxies, stars, and planets we see today. To help you picture this process, think of a vast field of flowers. If every flower symbolizes a point in the universe, then quantum fluctuations act like the wind, randomly gusting and causing some flowers to thrive more than others. These initial variations in growth are what enabled the formation of all cosmic structures, from the smallest asteroids to the largest galactic superclusters. In a universe without these subtle primordial differences, the complex tapestry of the cosmos would simply not exist. The importance of quantum fluctuations, however, goes far beyond just the creation of matter, as the idea is fundamentally connected to the true nature of the vacuum itself. In quantum mechanics, the vacuum is not a void of empty space, but is instead a realm brimming with latent potential. It is a dynamic stage where particles can spontaneously emerge from apparent nothingness, a revolutionary outlook that challenges our classical perception of reality and forces us to reconsider what we mean by nothing. Within our ongoing effort to comprehend the origins of the universe, quantum fluctuations provide us with a truly unique perspective. They guide our exploration into realms beyond the visible, pulling us into a subatomic world where the familiar laws of our daily experience dissolve into something far more exhilarating. This serves as a potent reminder that the reality we inhabit is infinitely more intricate and astonishing than what our senses are capable of perceiving. An especially compelling question then emerges: is it conceivable that our entire universe is nothing more than the outcome of one single quantum fluctuation? While such a notion might initially seem preposterous, a significant number of physicists and cosmologists now view it as a distinct possibility. If the cosmos did indeed begin as a tiny ripple in the quantum vacuum, then the very core of our existence could be fundamentally linked to these transient, unpredictable events. The progression of these ideas has pushed scientists to formulate increasingly elaborate and captivating models of cosmic genesis. For instance, the Big Bang theory, which proposes that the universe originated from an infinitesimally small and intensely hot point, now merges with quantum mechanics to give a much more cohesive narrative of our origins. This raises the question of just how far our understanding of the beginning of everything can truly go. As we probe deeper into these subjects, we find ourselves navigating a labyrinth of theories and concepts that defy our everyday intuition. The intricate relationship between quantum fluctuations and the expansion of the universe compels us to reflect on how everything we observe today was once a chaotic maelstrom of energy, a state where the impossible became reality. This journey encourages us to question not only the fabric of the universe, but also the very nature of our own being. Therefore, investigating quantum fluctuations has become an indispensable method for decoding the deepest mysteries of the cosmos. It forces us to look past the obvious and to embrace the idea that reality might be just as bizarre as it is magnificent. Every new discovery in this area moves us one step closer to grasping the fundamental fabric that binds everything together, from the most minuscule particles to the most remote galaxies. In this context, it is crucial to recognize that we are only just beginning to grasp the full extent of cosmological knowledge. As our understanding progresses, each answer we uncover seems to spawn a host of new questions, which in turn fuels the relentless fire of human curiosity. What other incredible surprises does the universe have in store for us? What secrets still lie concealed within the depths of the quantum vacuum? As we contemplate the immense scale of the cosmos, we should keep in mind that it all could have been initiated by a simple fluctuation, a single spark in the utter void of the vacuum. It is precisely these kinds of questions that compel us to continue our exploration and to dream of what lies beyond. The universe, with all its unsolved puzzles, is an open invitation to always venture further into the unknown. Quantum fluctuations are a fascinating aspect of reality that may sound like they belong in a work of science fiction, yet they are woven into the very structure of our universe. But what exactly are they, and why do they matter so much? To grasp this, you must first journey into the remarkable domain of quantum mechanics, a place where the governing principles are profoundly different from those that shape our daily lives. For a moment, try to imagine that the vacuum is not simply an absence of everything, but rather a space that is teeming with constant activity. In the quantum world, even this apparent emptiness is saturated with energy and potential. You can think of this quantum vacuum as a simmering cauldron. While it might seem inert on the surface, within it there is a ceaseless dance of particles that pop into and out of existence in the blink of an eye. This is the phenomenon known as a quantum fluctuation. These transient events are like bubbles forming and bursting within an immense sea of energy, allowing subatomic particles to appear and then vanish almost instantaneously. On occasion, these quantum bubbles can expand to a size where they become detectable. This transforms the vacuum into a dynamic stage where particles are constantly being created and destroyed, a process that underpins everything you know. If empty space is truly this busy, you might ask how we can be certain these fluctuations are real. Throughout the history of modern physics, scientists have developed theories and designed experiments that verify this very phenomenon. The energy of the vacuum, for example, has been confirmed indirectly through observations like the Casimir effect. This effect describes how two plates placed incredibly close together will feel a force of attraction, which is caused by the quantum fluctuations in the empty space between them. An experiment like this offers you a glimpse into the invisible reality that perpetually surrounds us, confirming that these fluctuations are far more than a mere curiosity of theoretical physics. They carry tangible consequences. These quantum events are thought to have been instrumental in the genesis of our universe. As the cosmos came into being, it's possible these tiny energy variations provided the initial seeds of matter, which would later coalesce to create galaxies, stars, and planets. In a way, you could say that every star you observe in the night sky might owe its origin to one of these minuscule energy bubbles in the primordial quantum vacuum. So why are quantum fluctuations so critical to our effort to comprehend the cosmos? The answer is found in their capacity to challenge your most basic assumptions about reality itself. They compel you to reconsider what you define as a vacuum or as nothingness. Quantum mechanics reveals a universe that is profoundly stranger than you can possibly conceive, a realm where conventional rules of logic seem to bend and shift. Furthermore, these fluctuations might contain the very solution to understanding concepts like dark matter and dark energy. While these forces are invisible to you, they seem to govern the fundamental structure and ongoing expansion of the universe. By figuring out how quantum fluctuations affect them, we could potentially solve some of the most profound puzzles in modern cosmology. The notion that our entire universe may have sprung from a single quantum fluctuation is truly captivating, but it also prompts some deep questions. If all that you perceive began from a minor variance in the vacuum, what does this imply about your sense of reality? Does this mean you share a direct connection to the quantum foam that birthed everything? As our research pushes forward, quantum physics consistently defies our intuition and beckons you to peer beyond the known limits of understanding. Quantum fluctuations show you that reality possesses a depth and complexity that is not immediately apparent. This phenomenon urges you to imagine a cosmos where all things are intertwined, and where the vacuum is not a void, but a cradle of infinite potential. The implications stretch far beyond physics, inviting you, from a philosophical standpoint, to contemplate the very essence of your existence. If the universe can materialize from nothing, what does this suggest about your own life and your role within the cosmos? For all of recorded history, humanity has been driven by a search for its origins. Quantum fluctuations provide a fresh perspective, lighting up a new path toward understanding how the universe was born. Although an immense amount remains to be uncovered, the study of this phenomenon gives you a portal into a hidden world, one brimming with mysteries we are still diligently working to decipher. Ultimately, quantum fluctuations represent more than just a compelling subject in modern science. They are an invitation for you to continue exploring and questioning. Every new insight in this area brings us nearer to solving the riddles of the cosmos, and, by extension, our own being. On this quest, you are not a passive spectator, but an engaged participant in the cosmic narrative that is constantly unfolding all around us. Have you ever stopped to think about how it all started? The concept that our universe had a distinct beginning is as intricate as it is enthralling. The Big Bang theory presents a powerful account of the cosmos's origin, but you may wonder what this term really signifies. In essence, it refers to the singular event that brought our universe into existence, a phenomenal expansion that took place approximately 13 billion years ago, 0.8 billion years ago. This story, however, is not simply one of explosive chaos. It is the chronicle of how everything you see today emerged from a point of infinite density. To help you picture the Big Bang, you can imagine it like a balloon. Before you inflate it, the balloon is just a tiny compressed point. As you add air, it expands and takes shape. In a similar fashion, the universe began as an incredibly hot and dense singularity that abruptly started expanding, creating all the matter and energy you know today. This was no simple occurrence. It was the very event that initiated time and space, converting a state of nothingness into everything. In the first few moments following the Big Bang, the universe rapidly expanded and cooled, which allowed for the formation of subatomic particles. This is a critical point to grasp, because these initial particles were the building blocks for all that followed, from stars and planets right down to you and me. The cosmos you inhabit would not exist without that original eruption of energy. Interestingly, the Big Bang wasn't a single, isolated moment in our cosmic timeline. The theory posits that, in its infancy, the universe underwent a phase known as cosmic inflation, a brief period of incredibly fast expansion that was vital in sculpting its structure. You can imagine the universe stretching exponentially in a mere fraction of a second. This initial burst of growth was essential for distributing matter evenly and stopping the young universe from collapsing back in on itself, reminding you that while the cosmos today appears immeasurably vast, it began as a place entirely beyond your everyday experience. In its earliest stages, the universe was a turbulent soup of particles and energy, a time when gravity and the other fundamental forces were just beginning to emerge. But you might ask how we can be certain of this. In the realm of science, evidence is everything. Physicists and astronomers have compiled a wealth of data from observing galaxies, analyzing the cosmic microwave background, and studying other celestial phenomena, all of which supports this model of a continuously evolving cosmos. Among the most compelling pieces of this cosmic puzzle is the cosmic microwave background radiation, which you can think of as a faint echo of the Big Bang itself, a signal that has traveled across the entire observable universe to reach us. Consider a bonfire that has died down, leaving behind only glowing embers. These remnants are all that is left of a once mighty fire. In much the same way, this background radiation is the afterglow of that primordial explosion, offering a unique fingerprint of the universe when it was merely a few 100,000 years old, providing invaluable data for scientists to piece together cosmic history. As the cosmos continued its relentless expansion and cooling, the very first atoms, hydrogen and helium, started to coalesce. This represented a pivotal moment, since these elements serve as the essential raw materials for stars. Without an abundance of hydrogen, neither stars nor galaxies could have ever formed. The process by which these first stars ignited involved immense clouds of gas collapsing under their own gravity over vast stretches of time, eventually sparking the initial nuclear reactions that would bathe the universe in light. It's truly extraordinary to consider that every star you see twinkling in the night sky and every galaxy we can observe ultimately traces its lineage back to this singular, cataclysmic event billions of years ago. However, as the universe expanded, it also cooled, which permitted more complex structures to take shape. But the universe's story is filled with unexpected developments, including the appearance of dark matter and dark energy, mysterious components that now appear to govern the cosmos. Dark matter is a crucial substance that remains invisible to us, yet we can infer its existence from the gravitational effects it has on visible matter. Dark energy, by contrast, is an even greater puzzle, behaving like a pervasive force that is actually accelerating the expansion of the universe. You can imagine these two phenomena as unseen puppeteers in a grand cosmic drama, subtly shaping the destiny of the universe and everything within it. Albert Einstein's general theory of relativity gives us a conceptual toolkit for comprehending how gravity governs the interactions between matter and energy throughout the cosmos. This theory allows us to model how the vast structures of the universe form and evolve over cosmic timescales, serving as a powerful reminder that we live in a dynamic system where every event has consequences and every celestial body has its own unique story. As you contemplate these concepts, it's vital to recognize that the Big Bang is more than just a scientific theory. It stands as a monument to our innate curiosity and our profound drive to understand where we come from. The questions surrounding our origins are both deep and eternal, and each answer we uncover only seems to lead to more complex inquiries, pushing us to wonder what might lie beyond the Big Bang, or if other universes could possibly exist. These questions beckon us to press onward, to continue our exploration, and our search for knowledge within an endless sea of possibilities. The narrative of the Big Bang is truly just the opening chapter in a much grander story. With every new discovery in cosmology, we open fresh avenues of understanding, revealing a universe brimming with surprises and marvels, and each step we take brings us closer to grasping our true place within it all. Cosmic inflation is a notion so astounding that it can almost feel like something out of science fiction. How could it be that the universe, which you perceive today as so immense and ever-expanding, originated from something so infinitesimally small and dense? The very idea that the cosmos swelled at a speed beyond comprehension in just a fleeting instant is nothing short of breathtaking. To grasp what cosmic inflation truly entails, it helps to visualize a balloon. It begins as a tiny object, but as you pump air into it, its surface expands with incredible speed. A very similar process is thought to have occurred in the primeval universe. In the first fraction of a second after the Big Bang, the cosmos is believed to have undergone a period of exponential growth, ballooning from the size of a subatomic particle to encompass everything we can observe today, all in a fraction of a moment. This event not only clarifies why the universe has its current appearance, but also elegantly solves several long-standing cosmological puzzles. One of the most significant of these puzzles is the remarkable uniformity of the cosmos. When you gaze out into space, you can observe regions that are incredibly far apart, yet they exhibit nearly identical temperatures and densities. Cosmic inflation proposes a solution. Prior to this explosive growth, these disparate regions were actually in close contact, allowing them to exchange energy and achieve a state of equilibrium. In essence, every part of the universe originated from a single point before being rapidly pushed apart. This prompts an intriguing question. What could have possibly powered such a sudden and massive expansion? Scientists theorize that a unique form of energy, often called vacuum energy, or the inflaton field, may have permeated the infant universe. This energy would have possessed the remarkable property of pushing space itself outward, causing the cosmos to inflate. Eventually, this energy is thought to have transformed into the matter and radiation we see today, allowing the universe to continue expanding at a much more moderate pace. Finally, this leads us to consider how this inflationary period shaped the structure of the universe we inhabit. The answer is found in the microscopic quantum fluctuations that were present during this era. Imagine the smooth surface of a pond. If you were to toss a pebble into it, you would create ripples that propagate outward. In a comparable way, tiny quantum irregularities during inflation were stretched to astronomical scales, creating slight variations in the density of the early universe. These variations acted as the primordial seeds from which all galaxies and large-scale structures would eventually grow. As the cosmos stretched outwards, these initial fluctuations evolved into zones where matter began to coalesce, eventually giving birth to stars and entire galaxies. It's plausible that without this inflationary period, you would never witness a universe adorned with the magnificent galaxies we observe today, a process that illuminates the distribution of matter and energy across space. But what impact does this have on our concept of time? Cosmic inflation presents a radically new lens through which to view time itself. In the universe's very first moments, the time you experience might have been a completely different phenomenon. With such a rapid expansion, space and time became interwoven in a manner we are still striving to fully grasp, prompting profound philosophical inquiries. Is time a fundamental constant, or is its nature contingent on the state of the universe? Perhaps one of the most mind-bending outcomes of cosmic inflation is its relationship with the multiverse theory. If our own universe underwent such an explosive expansion, it begs the question of whether other universes might also exist, each governed by its unique set of physical laws and properties. While this concept may sound like something from science fiction, many physicists treat it as a genuine possibility, unlocking a vast array of questions about our own existence and where we fit within the grand cosmos. Cosmic inflation does more than just help us decode the universe's past. It also equips us with the means to peer into its future. By analyzing the subtle variations left behind by this event, we can formulate predictions about how the universe will continue to evolve. Will its expansion persist indefinitely, or will it eventually slow down and lead to a cosmic contraction? These are the monumental questions that scientists are diligently working to resolve. Despite its inherent complexity, cosmic inflation moves us closer to solving the universe's most profound puzzles. It compels you to contemplate the origins of everything you see and motivates us to relentlessly search for more answers. I wonder if we are on the brink of a revolutionary discovery that could entirely reshape our perception of the cosmos. Ultimately, cosmic inflation is a staggering event that transformed a microscopic universe into the immense reality you now inhabit, answering many of our deepest questions while simultaneously creating new ones, and reminding us that the quest for knowledge is an endless journey. The connection between quantum mechanics and cosmology feels like a delicate, unseen thread that joins the smallest constituents of matter to the boundless universe that envelops you. At this captivating intersection, the principles that command the subatomic realm offer us vital clues to unraveling cosmic enigmas. But how exactly do the foundations of quantum mechanics shape our comprehension of the universe? Let's start by picturing quantum mechanics as a rulebook for a stage where particles are not solid, predictable entities, but more like actors in a surreal play where any outcome is possible. In this quantum theater, particles can materialize and vanish, with their locations and speeds governed by the laws of probability. Can you envision a coin that, rather than landing on heads or tails, exists in a continuous state of indecision, as if it were spinning for all eternity? This very uncertainty is the core of quantum mechanics. So, how does this relate to cosmology? If you accept that the universe originated from a singularity, a point of immeasurable density, then quantum mechanics implies that uncertainty and chaos reigned even in those initial moments of creation, where quantum fluctuations were the sparks that eventually sculpted the vast cosmic structures you see. These quantum fluctuations are like fleeting bubbles in an ocean of pure potential, appearing and disappearing in an instant, yet capable of leaving a permanent impression on the very fabric of space-time. But how do such minuscule disturbances translate into structures as massive as galaxies? The solution is found in the interplay between these fluctuations and the cosmic forces of dark energy and gravity. Imagine each quantum fluctuation as a tiny pebble tossed into a still pond. The resulting ripples create intricate patterns on the water's surface. In a similar way, these quantum events introduced variations in the universe's density, which became the essential seeds that gravity would nurture into the galaxies and galactic clusters we observe today. What I find particularly fascinating about this link is the notion that quantum mechanics not only influences the universe on a grand scale, but also gives us a framework to understand its development through the ages. The laws of quantum mechanics are integral to the formation of the particles that compose all matter, and the interactions between these particles dictate the entire history of the cosmos. Isn't it extraordinary to consider that in the universe's infancy, the very same physical laws governing the most minute aspects of our existence were also responsible for creating the most magnificent cosmic tapestries? This bond between quantum mechanics and cosmology also forces you to reconsider the fundamental nature of time and space. If the universe erupted into being from an explosion of energy and particles, what was that first instant truly like? Some scientists propose that time as you understand it might have been born in that very moment of creation. In this view, quantum mechanics helps answer not only how we came to be, but also offers insights into why we exist at all. As our understanding of the cosmos deepens, it's crucial to recognize that quantum mechanics and cosmology are two faces of a single reality. While one field delves into the infinitely small, the other invites you to marvel at the sheer immensity of the universe. When brought together, these disciplines empower us to explore the most fundamental questions about our place in the cosmos and the true nature of existence, challenging our deepest intuitions about the world. It can be perplexing to accept that our universe might stem from random quantum events. This randomness, however, isn't synonymous with total chaos. Instead, it points to an underlying order that guides cosmic evolution, even if it's not immediately apparent. In light of this, the possibilities that stretch out before us are truly thrilling. Quantum mechanics encourages you to entertain the notion of alternate realities and a multiverse, where every choice or event could branch into a different outcome, challenging our very perception of reality and our place within it. When you gaze upon the night sky, it's worth remembering that each star and every galaxy is the product of an intricate interplay between quantum mechanics and cosmic scale. This field of science is far more than a specialized discipline. It serves as a gateway to the most profound enigmas of existence. By grasping how these minuscule fluctuations shaped the immense cosmos, you and I get a bit closer to answering the ultimate questions of why we are here and how we became a part of this magnificent universe. Have you ever truly considered what is concealed within the vacuum of space? You might imagine that emptiness is just a void, a place where nothing exists. But the world of quantum mechanics presents an entirely different picture. In this extraordinary realm, what we call empty space is actually a vibrant ocean of activity. This brings us to the concept of the quantum vacuum, an idea that, while seemingly strange, carries deep implications for how we comprehend the cosmos. Picture a perfectly still lake. Its surface appears calm and unmoving, yet underneath, hidden currents flow and bubbles continuously form and dissipate. The quantum vacuum behaves in a similar fashion, filled with fluctuations that are invisible to us but are constantly taking place. These disturbances are fleeting and almost undetectable, yet they possess the power to exert a colossal influence on the universe's structure. So, what are these quantum fluctuations? Precisely. They are essentially temporary shifts in the energy level of the vacuum. According to quantum theory, the vacuum is not a state of absolute zero energy. On the contrary, it is teeming with virtual particles that pop into existence and vanish in the blink of an eye. Although these particles differ from those we are familiar with and cannot be measured conventionally, their existence is crucial for understanding the universe's most fundamental operations. This reality prompts a fascinating question. If the vacuum is so full of activity, could that energy lead to something much larger? The surprising answer is yes. Under the right circumstances, these fluctuations can give rise to actual particles. In the very early universe, just after the Big Bang, it's plausible that these quantum shifts were responsible for forging the matter that now constitutes everything you see around you, as if the vacuum held a latent potential waiting to be unleashed. The revelation that the quantum vacuum is so dynamic compels us to reevaluate the very nature of what is real. If the vacuum is a site of perpetual creation and annihilation, does it follow that everything in our world is the outcome of these tiny, bubbling pockets of energy? It's a captivating notion that confronts our conventional ideas about the substance of matter. We often see a vacuum as the antithesis of existence, but quantum mechanics shows us that it is actually a fertile ground of possibility. This insight leads to yet another profound question. What else might emerge from this vacuum? Some scientists propose the existence of multiple universes, with each one originating from a unique quantum fluctuation. In this view, the vacuum could function as a sort of cosmic nursery, where new universes are constantly being born. The link between the quantum vacuum and the creation of particles also has major implications for our understanding of energy. suggesting it is not fixed, but can materialize from nothing. Furthermore, the quantum vacuum doesn't just produce particles, it also plays a critical role in how they interact with one another, as these virtual particles can influence the fundamental forces that govern the cosmos. This means the vacuum is not merely a passive backdrop for events, but an active agent shaping the cosmic story. Its connection to gravity is another fascinating frontier, as the interaction between this powerful force and the quantum vacuum may unlock secrets about the fabric of space and time, potentially holding the key to a unified theory of physics. As we probe deeper into the quantum vacuum, we inevitably face profound philosophical questions. If the universe can materialize from nothing, what does that imply for our traditional concepts of creation and origin? Perhaps the very essence of the cosmos is tied to the idea that nothing is ever truly empty. Exploring these fluctuations is a captivating journey, where each discovery opens up new lines of inquiry, bringing us closer to unraveling the mysteries of the void we inhabit. So, the next time you look up at the stars, remember there is so much more at play than what meets the eye. Within the immense realm of what is possible, quantum fluctuations serve as the very catalyst for creation, showing us that the cosmos is filled with wonder, even where matter does not exist. When you look up at the night sky, you might find yourself asking what process led to the formation of stars and planets. The journey to that answer introduces you to the remarkable idea of quantum fluctuations. But how can such minuscule tremors in the vacuum give rise to something as magnificent as the particles that compose our entire universe? You can think of quantum fluctuations as fleeting ripples that momentarily emerge from the void before disappearing. Picture a perfectly still ocean from which a small wave suddenly materializes, only to recede back into nothingness an instant later. This very process unfolds at the most fundamental scale of reality, where quantum mechanics dictates the rules of particle behavior. To understand what this means for particle creation in the early universe, you must envision a cosmos at its inception, brimming with immense energy and boundless potential. In this incredibly dense and heated state, quantum fluctuations were like sparks, igniting the process of creation. Imagine a pot of boiling water. The bubbles that form and rise are much like these cosmic fluctuations, each one representing a potential particle that could spring into being. So how did these quantum potentials transition into the tangible matter we know? As the universe underwent a period of explosive growth called cosmic inflation, these fluctuations and their associated energy were effectively frozen into more permanent configurations. This transformation, which gave birth to the particles of matter, is much like water vapor cooling and condensing into droplets of rain. In this way, ephemeral quantum tremors solidified into the substance of today's universe. In the primordial cosmos, energy and chaos were the defining characteristics. Quantum fluctuations were essential not just for generating particles, but also for helping to create the conditions that allowed matter to organize into far more intricate structures. The key to this organization lies in the concept of symmetry, and more importantly, the breaking of that symmetry. In physics, symmetry suggests a state of perfect harmony and balance, like a flawlessly drawn pattern where every part is uniform and predictable. When this perfect symmetry is disrupted, however, the fundamental forces that govern the universe can emerge. In the context of quantum fluctuations, the act of symmetry breaking enabled certain particles to gain mass while others did not. This critical distinction is essential for comprehending how the initial chaos of the universe eventually gave way to the formation of galaxies and stars. Some advanced frameworks, like string theory, propose that we may inhabit a multiverse, a cosmic landscape where every single quantum fluctuation could potentially spawn an entirely new universe. In this view, each ripple in the quantum sea is a doorway to another reality, complete with its own distinct physical laws and properties. Contemplating such a possibility forces you to question the very nature of our own existence. Beyond just creating particles, quantum fluctuations also redefine our understanding of the vacuum itself. Far from being an empty void, the quantum vacuum is a dynamic space teeming with potential, where particles can continuously appear and vanish. This concept of a vibrant, energetic vacuum is crucial for grasping how pure energy can manifest as physical matter, with each newly formed particle adding to the fabric of reality. As countless particles emerged, gravity began to exert its influence, pulling these fundamental building blocks together to form the vast cosmic structures we observe today, including galaxies and massive galaxy clusters. Furthermore, quantum fluctuations are suspected to be connected to dark matter and dark energy, the two greatest mysteries in modern cosmology. The accelerating expansion of the universe, driven by dark energy, might be linked to the inherent energy of the vacuum, suggesting it plays an active role in cosmic evolution. Ultimately, this reveals a profound cycle. Quantum fluctuations give rise to particles, and these particles form the matter and energy that define the cosmos. For you, this means that on the most fundamental level, you are an integral part of this cosmic story. Each of us is the product of those initial quantum ripples that emerged from the void and, through a complex dance of forces and energy, sculpted the world we inhabit. Considering the origin of particles from quantum fluctuations is more than a scientific exercise. It is an invitation to contemplate your own place within the cosmos. The next time you gaze at the stars, remember that everything you see, every planet, every distant sun, and even yourself, is the result of a universe born from quantum chaos. The cosmos remains a place of deep secrets, and quantum fluctuations are one of the keys to unlocking them. So, as you reflect on the sheer scale of the universe, keep in mind that its origin hinged on a single moment when these tiny quantum tremors took the first decisive step toward creating everything we now know and are. It is truly astonishing to consider that all of this could have emerged from what was once nothing. Within the vast fields of physics and cosmology, the principles of symmetry and its breaking are foundational to our theories about the universe's birth and development. To grasp what symmetry means in this context, picture an object in perfect equilibrium, such as a sphere. A sphere is completely symmetrical. No single point on its surface is different from any other. This ideal balance is mirrored in many of the laws of nature, which describe forces and particles behaving in consistent and predictable ways. But the story becomes truly interesting when that perfect symmetry is broken, a phenomenon that allows for the emergence of new and complex realities, much like how the ordered, symmetrical structure of ice forms from liquid water. When you heat ice, for instance, it melts and its symmetrical structure is lost as it becomes water, a state of greater disorder. This simple change illustrates how, within the universe, the shattering of symmetry can give rise to completely new and different conditions. In the realm of physics, this idea becomes even more fascinating, as symmetry in nature is typically linked to the conservation of properties like energy or electric charge. When that symmetry is broken, however, truly unexpected phenomena can surface. A prime example of this is the symmetry breaking that took place in the early universe, just moments after the Big Bang. At that instant, everything was seemingly chaotic, yet this very disruption enabled the formation of fundamental particles, which are the building blocks of the matter you see today. The question this prompts is clear. how does this phenomenon actually contribute to the creation of the universe we inhabit? As the cosmos expanded and cooled, its conditions underwent a dramatic transformation. The fundamental forces, which were initially indistinguishable, began to separate in a process called symmetry breaking, which in turn allowed particles to acquire mass. This was an absolutely essential step in the creation of matter. Without this break, particles would have lacked the properties needed to form atoms, meaning that matter as you understand it would simply not exist. So, what part does quantum mechanics play in all of this? On a subatomic scale, particles can behave in very strange ways. Quantum theory shows us that, under specific circumstances, particles can exist in many states at once, a phenomenon referred to as superposition. This principle is tied to symmetry breaking because particles interacting within the quantum vacuum can flicker in and out of existence, weaving a fabric of potential realities which, once symmetry is broken, give rise to the tangible matter of our world. Picture a chess game where every piece is perfectly arranged and untouched, a situation of pure symmetry. The moment one player makes a move, that symmetry is shattered, and the game is transformed, opening up countless new strategies and possibilities. In the same way, symmetry breaking in the universe is like that first move, enabling new realities where particles could interact in ways that were previously impossible. When you delve deeper into this concept, a compelling question arises. What if symmetry had been broken in a different way? Such a change could have produced a universe completely unlike our own. The array of particles and forces that you observe today is the outcome of a very fine balance between symmetry and its violation. And this principle doesn't just apply to particles. The very structure of the cosmos, from galaxies down to stars, originates from these fundamental interactions. Moreover, symmetry breaking is also connected to the unified field theory, which seeks to explain how the different forces of nature are all related. This theory proposes that, in their original state, all forces were merged into a single one. As symmetry was broken, these forces began to emerge individually, resulting in gravity, electromagnetism, and the nuclear forces. It's a complex process, but it is fundamental to understanding how our universe operates. Nature offers us endless examples of how breaking symmetry can produce unexpected results. In particle physics, for example, we have observed phenomena like the Higgs boson. This fundamental particle, which is responsible for giving other particles their mass, was confirmed in 2014 and stands as a powerful testament to how symmetry breaking can unveil hidden aspects of nature that were once completely invisible to us. As you continue to explore the field of cosmology, it's fascinating to consider how symmetry and its disruption have not only physical, but also profound philosophical implications. The notion that our universe may have emerged from a state of perfect symmetry, only for it to break and allow for the diversity you see around you, raises deep questions about the very nature of reality and your own place within it. Ultimately, symmetry breaking is a cornerstone concept that helps you grasp the universe's complexity. From the birth of particles to the evolution of the fundamental forces, this phenomenon reveals how apparent chaos can actually be the catalyst for incredible order. As science advances, we continue to unravel the secrets of how symmetry and its violations shape our cosmos, providing fresh perspectives on the origins of everything you know. With every new discovery, you move a little closer to understanding the magnificence of the universe and your role in it. String theory is an enthralling idea that has sparked the imagination of many people, not just physicists, but anyone curious about the cosmos. But what is string theory, precisely? And what is its connection to the multiverse and quantum fluctuations? To begin to understand this, you must first picture the basic constituents of nature, those that make up matter and the forces you know, not as tiny dots, but as minuscule, vibrating strings. These strings, which are unfathomably small, are capable of vibrating in various ways, and each distinct mode of vibration corresponds to a different particle. So, rather than viewing electrons and quarks as separate objects, you can imagine them as different musical notes produced by the very same kind of string. Isn't that an amazing thought? This perspective not only offers a new way to see physics, but also implies that more dimensions might exist in the universe than you can perceive. So, where do quantum fluctuations fit into this picture? These tiny, spontaneous variations in the quantum vacuum could be the very engine that generates these strings. Think of the vacuum as an immense ocean of pure potential. Within this ocean, strings can pop into and out of existence, forging a reality that is in constant flux. This leads to the captivating idea that our universe could be just one of many realities to emerge from these fluctuations. And what about the multiverse? The multiverse hypothesis suggests that countless universes exist, each with its own distinct set of physical laws and its own reality. While some of these universes might be quite similar to ours, others could be fundamentally and unimaginably different. Could you conceive of a cosmos where gravity is so intense that time itself comes to a halt? Or another where the very principles of chemistry forbid life as we understand it from ever forming? The concepts of string theory and the multiverse are far from mere abstract musings. They are serious scientific efforts to forge a unified theory of physics. The ambition of string theory is to reconcile quantum mechanics, the science governing the subatomic realm, with general relativity, the framework that explains gravity and the universe on its grandest scale. The multiverse, in this context, can be seen as a natural outcome of the different ways these fundamental strings can vibrate across various universes. Consider how a single musical composition can be performed in countless styles. Similarly, vibrating strings could give rise to a limitless assortment of universes. Every one of these cosmic interpretations would be distinct, directly shaping the kinds of matter and life that could possibly emerge within it. Have you ever contemplated the existence of a universe where the physical laws permit beings of a completely different nature from ourselves? This notion that our own universe is just one among many presents us with profound philosophical dilemmas. If an infinite number of universes exist, what does this imply for our own existence? Are we uniquely special in a boundless ocean of realities? Or are we merely a chance occurrence in a vast cosmic lottery? With every new insight from particle physics and cosmology, scientists gather more potential evidence supporting string theory and the multiverse. Experiments conducted at particle accelerators, like the Large Hadron Collider, or LHC, are designed to penetrate the deep mysteries that envelop us, as each particle collision offers a potential glimpse into new dimensions and other realities. In parallel, string theory has introduced a fresh set of questions concerning the fundamental nature of space and time. If extra dimensions are real, how might that alter our very perception of reality? And could it ever be feasible to journey between these universes, or even across the different dimensions of our own? The discipline of cosmology is in a state of continuous transformation, with new theories and findings appearing with remarkable frequency, each one advancing our comprehension of the cosmos's complexity. String theory and the multiverse idea are key components of this intricate puzzle. They are especially vital for grasping the part that quantum fluctuations played in the very creation of our universe. Ultimately, it is crucial to consider how these concepts reshape our perception of reality. If the universe truly arises from the vibrations of invisible strings and quantum-level jitters, then our entire existence, our consciousness, and even our feelings might just be the product of a fine-tuned equilibrium within an unimaginably vast and complex system. Contemplations like these deepen our appreciation for the sheer wonder of the cosmos and intensify our innate drive for knowledge.
So when you think about string theory and the multiverse, which is the hypothetical collection of all conceivable universes, it's important to recognize that each discovery brings us a step closer to the truth. Even though a great deal remains unknown, every question we pose moves us nearer to solving the enigma of the universe and understanding our own place within it.
What exactly is the enigmatic cosmic microwave background, often referred to as relic radiation, that permeates the entire universe? And why is it so essential for comprehending the origins of the cosmos? Let's explore this captivating subject. Picture the universe as an immense, completely dark chamber. If you were to switch on an incredibly faint light, you would see it diffuse in every direction. This is analogous to the behavior of the cosmic microwave background radiation, which acts like a persistent echo of the Big Bang, the initial event that sparked all of creation.
But how can we be certain this radiation is real? And what does it reveal about our universe? Back in 1965, two scientists named Arno Penzias and Robert Wilson were conducting research when they detected a constant, low-level hiss in their radio antenna. Unbeknownst to them at the time, they had stumbled upon something truly historic: the cosmic microwave background radiation. This serendipitous find not only secured them a Nobel Prize, but also furnished some of the most powerful evidence for the Big Bang theory.
What makes this radiation so profoundly important? The cosmic microwave background serves as a snapshot of the universe in its infancy, just 300,000 years after the Big Bang. During that era, the cosmos was a ferociously hot and dense environment, swarming with charged particles. As the universe expanded, it also cooled, which allowed electrons and protons to finally bind together into atoms. This event, which scientists call recombination, unleashed a flood of photons that have been traveling through space ever since, giving us a direct portal to the distant past. Just imagine having the ability to gaze backward through time. This is precisely what the background radiation enables us to do, informing us about the universe's state in its earliest phases and unveiling specifics about its composition and structure. Yet, there is even more to learn from this ancient light. While the cosmic microwave background is remarkably uniform across the sky, it does feature minuscule variations that hold fundamental importance, as these tiny fluctuations map out how matter was originally spread throughout the primordial universe. Consider this radiation as a blueprint that allows us to trace how galaxies formed and gathered into clusters over billions of years. In a universe without these slight imperfections, the cosmos would look drastically different, possibly being a void devoid of stars and planets. This brings up the question of how this relates to the quantum fluctuations mentioned earlier. It is truly remarkable to think that these slight temperature differences in the background radiation are likely tied to quantum events that took place at the dawn of time. It feels as though these seemingly negligible quantum fluctuations planted the seeds for everything that we can observe in the universe today. Is it not extraordinary to contemplate such a direct and powerful link between the laws of quantum physics and the formation of the entire cosmos? Scientists have dedicated themselves to meticulously studying this radiation, employing sophisticated telescopes capable of perceiving the most subtle temperature variations in this cosmic afterglow. These observations have empowered scientists to chart the universe on a scale that was previously unimaginable, allowing you to confront some of the most fundamental questions. We can now ask how much of the cosmos is made of the visible matter you see, how much consists of elusive dark matter, and what role is played by dark energy, the force seemingly causing the universe's expansion to speed up. Each time you look at the stars in the night sky, you are actually observing the culmination of billions of years of cosmic history. The cosmic microwave background serves as a persistent reminder that the universe has an incredibly rich and intricate past. It encourages you to contemplate your own position within this vast expanse, and to wonder how everything you know today could have emerged from the tiniest fluctuations at the dawn of time. As researchers delve deeper into this relic radiation, they uncover new lines of inquiry. Could this information ever help you solve the puzzles of a potential multiverse? What further secrets about the fundamental nature of reality might the background radiation hold? This cosmic microwave background is far more than an echo of a bygone era. It is a vital tool that helps you comprehend the present and possibly even forecast the future of the cosmos. This reminds you that the universe is a dynamic and constantly evolving arena, filled with mysteries and surprises that await discovery. To think about the cosmic microwave background is to contemplate the entire history of the universe, a narrative of expansion, transformation, and profound wonder. So, the next time you find yourself gazing at the star-filled sky, remember that the faint resonance of the Big Bang is still there, a sign that you are part of a cosmic story much grander than you can conceive. What is our universe truly composed of? When you observe your surroundings, it becomes clear that there is more at play than what is immediately apparent. Dark matter and dark energy are two ideas that fundamentally challenge your comprehension of yourself and the world around you. So, let's explore what these cryptic components of the cosmos actually are. Dark matter is a form of matter that is completely invisible, as it neither produces nor reflects any light, which makes it nearly impossible to detect with conventional instruments. So how can you be certain it exists? Picture a dance taking place in a pitch-black room. You can hear the music, but the dancers are unseen. However, by watching how shadows are cast and how light moves between them, you can deduce that people are present. In a similar fashion, scientists have noted that galaxies move in ways that cannot be accounted for by their visible matter, which strongly implies the presence of something more. What many are convinced is dark matter. Dark energy, in contrast, is an even more perplexing phenomenon. Imagine you are blowing up a balloon, causing it to expand. Now, what if I were to tell you that the universe is undergoing a similar expansion? In fact, current observations confirm not only that the universe is expanding, but that this expansion is actually accelerating. This is the role attributed to dark energy, the mysterious force driving this accelerated growth. Much like an unseen current of air inflating the balloon, dark energy is the agent enabling the universe's continued expansion. Now, you should consider what this reveals about your understanding of the cosmos. The visible matter you are familiar with, like stars and planets, represents just a tiny fraction of the universe's total makeup. Dark matter constitutes approximately 25%, while dark energy dominates with about 70%. This realization forces you to question your perception of what is real, and to ask how your understanding of the universe must change when you accept that you are surrounded by things you cannot perceive. Dark matter is believed to have played a vital role in the formation of the universe. Think of it like building a house, where a solid foundation is essential for stability. Dark matter served as this cosmic foundation, providing the gravitational framework necessary for galaxies and other celestial objects to clump together and form the complex structures you see today. Without it, the universe would be a profoundly different, perhaps even empty, place.
But you might wonder how this ties into the theory of cosmic inflation. This theory proposes that in the very first moments after the Big Bang, the universe underwent a period of exponential growth. During this intense expansion, it is thought that quantum fluctuations were stretched to cosmic scales, giving rise to both dark matter and the seeds of the structures that now exist. This suggests that every galaxy and twinkling star you can see may have originated from these infinitesimal ancient ripples. While studying dark matter and dark energy directly is incredibly difficult, astronomers have developed indirect methods to confirm their existence. By carefully observing the light from galaxies and their motions within clusters, they can map the gravitational influence of dark matter. It is analogous to watching a river. Though you cannot see the currents beneath the surface, you can infer their presence and strength by observing the behavior of the water on top. Still, a great many questions continue to go unanswered. What is dark matter actually made of? Some scientists theorize that it consists of entirely new particles that have yet to be discovered. Alternative ideas suggest it might be a novel manifestation of gravity that only becomes apparent on immense scales. The possibility of different kinds of dark matter also remains, and the scientific search for these answers is very much active. Dark energy also prompts profound questions about the universe's nature and ultimate fate. If this force is indeed causing an accelerated expansion, are you living in a cosmos destined to expand into infinity? Alternatively, could there be a point when the gravitational pull of dark matter becomes dominant, causing the universe to reverse course and collapse? These are fascinating questions that compel you to reflect on the future of our cosmos. On a philosophical plane, the reality of dark matter and dark energy urges you to reconsider your perception of reality itself. If the vast majority of the universe remains invisible and unknown, what does that imply for your entire quest for knowledge? It forces you to ask if you are truly prepared to accept that there is fundamentally more to the universe than you can ever directly perceive. The scientific investigation into dark matter and dark energy is a rapidly advancing field. New experiments and more precise observations are continuously providing fresh insights into these cosmic enigmas. As your collective understanding grows, each new discovery holds the power to reshape your view of the universe and your own place within its grand design. The next time you find yourself gazing at the night sky, I want you to consider that for all the brilliant stars you see, the vast majority of the cosmos is completely invisible to us. The existence of dark matter and dark energy serves as a powerful reminder that reality is infinitely more intricate and astonishing than our imaginations could ever grasp. General relativity, which stands as one of Albert Einstein's crowning achievements, fundamentally altered how we perceive the universe. So, what exactly is this theory, and what makes it so indispensable to contemporary cosmology? In the moments ahead, we will delve into how general relativity equips us to decode the deepest enigmas of the cosmos. To begin, let's re-examine our concept of gravity. You have certainly felt its effects your entire life. Whenever you jump, you are reliably pulled back to Earth. In the framework of general relativity, however, gravity is not merely a force exchanged between objects. Instead, it is understood as the curvature of spacetime, the very fabric of reality, which is warped by the presence of mass and energy. Consequently, when you observe a planet or a star, what you are actually witnessing is the way its immense mass distorts the space-time surrounding it. You can visualize this by imagining a heavy bowling ball placed on a trampoline, causing the surface to sag. If you then roll a marble nearby, it will naturally follow the curve and move toward the ball, which is precisely how gravity operates on a cosmic scale.
But how does this principle apply to the universe in its entirety? As we trace our cosmos back to the Big Bang, it's crucial to realize that the universe isn't simply expanding. According to general relativity, this expansion is governed by the curvature of spacetime and is therefore not uniform. The rate can change based on the density of matter, with greater mass creating a more pronounced curve that can either slow the expansion down or accelerate it, directly influencing the universe's ultimate fate. This brings us to the fascinating concept of black holes, whose existence is a direct prediction of general relativity. These enigmatic objects are formed when a truly massive star collapses in on itself, generating a gravitational pull so immense that it creates a point of no return from which nothing, not even light, can escape. Theorists suggest that at the very center of a black hole, our current laws of physics may completely break down, forcing us to speculate on the fundamental nature of reality itself. Another mind-bending consequence of general relativity involves its relationship with time. Within this theory, time is not a constant, universal river flowing at a steady pace. Rather, its flow can be stretched or compressed by gravity. To make this clear, picture a pair of twins. One stays on Earth, while the other travels to the vicinity of a black hole. For the twin near the immense gravity, time would pass much more slowly. And upon reuniting, this twin would be significantly younger. This effect, which is known as time dilation, compels us to completely rethink our intuitive understanding of time. General relativity has also been rigorously confirmed through direct astronomical observation. One of the most celebrated tests was the solar eclipse experiment of 1919, which demonstrated that light from distant stars bends as it passes by the sun, exactly as Einstein's calculations foretold. Beyond making Einstein a global celebrity, this confirmation paved the way for predicting other phenomena, such as gravitational waves, which were first detected in 2015. These ripples in spacetime, caused by cataclysmic events like merging black holes, have opened up an entirely new way for us to perceive the universe. It is important to recognize, however, that general relativity isn't our only framework for understanding gravity. On the subatomic level, in the quantum realm, gravity's behavior appears to be different. The principles of quantum mechanics, which dictate the strange rules governing tiny particles, do not currently harmonize with general relativity. This fundamental conflict has spurred a generations-long scientific search for a unified theory that can seamlessly merge gravity on cosmic scales with quantum phenomena. As we look toward the future, the questions about the cosmos only grow more profound. If general relativity accurately describes the behavior of space and time, what might happen if we were to discover dimensions beyond our three-dimensional perception? Ideas like string theory, which proposes that all fundamental particles are just minuscule vibrating strings, hint that we may inhabit a universe far more complex than we can currently see. General relativity thus not only illuminates our present, but also frames the most critical questions about the universe's destiny. Will it expand forever? Collapse in a big crunch? Or could our reality be just one of countless others in a vast multiverse? Ultimately, our innate human curiosity compels us to find answers, and general relativity stands as one of the most powerful instruments we have for solving these grand puzzles. It remains a cornerstone of our modern cosmic perspective, giving us the intellectual tools to understand the interplay of gravity and time, while simultaneously revealing even deeper questions that await answers. As our exploration of the cosmos continues, it is this cycle of questioning and discovery that truly defines our scientific journey, with each new answer unveiling a universe of new questions. So, what proof do we actually have for the Big Bang Theory and the associated quantum fluctuations that supposedly started it all? While this is one of cosmology's most captivating questions, it can also feel quite daunting. To simplify it, let's imagine the entire universe is a single, immense book, where every galaxy, star, and particle is a word on its pages. How can we be certain that this cosmic story truly began with the Big Bang? A crucial clue is the cosmic microwave background radiation, also known as relic radiation, which is a faint thermal glow that permeates all of space.
Consider the possibility that a faint glow from the Big Bang has persisted, a light that we are still able to detect in the present day. This radiation serves as a reverberation from the instant the universe came into being, almost as if creation itself is sharing its secrets with us through this luminescence. The cosmic microwave background is essentially a snapshot of the cosmos in its earliest moments, a time when it was an incredibly hot and dense environment. As the universe expanded, this primordial light was stretched and cooled, which allows us to observe it today with our sophisticated scientific instruments. So, what is the ultimate significance of this discovery? It provides compelling evidence that the universe indeed had a starting point, a beginning that aligns perfectly with the tenets of the Big Bang theory. But then, you must consider the role of quantum fluctuations. These minuscule ripples within the quantum vacuum are fundamental to grasping how all the structures in the universe originally took shape. Picture a perfectly still body of water that suddenly develops tiny waves. These are analogous to quantum fluctuations, minor disturbances with the potential to evolve into something far more significant. Within the cosmic framework, these initial fluctuations acted as the very seeds from which galaxies and entire galactic clusters would eventually grow. The connection that scientists have uncovered between the cosmic microwave background radiation and these quantum fluctuations is truly astonishing. They found that the slight variations in temperature across this ancient radiation directly correspond to the disturbances that were present in the primeval universe. In effect, these tiny quantum ripples were the catalyst for everything you see around you today. But how do these empirical observations fit into the broader theories that seek to explain the universe's origin? When you gaze at the night sky and see the countless galaxies, you are witnessing more than just distant points of light. The existence of each galaxy is the result of a formative process, one that is intrinsically tied to the expansion of the universe that started with the Big Bang. Studying these distant galaxies and their distribution throughout space tells us a detailed story about the universe's expansion and its evolution through the ages. Through the careful study of these galaxies, scientists have verified not only that the universe is expanding, but that its expansion is actually accelerating. This revelation, in turn, introduces new and profound questions regarding the true nature of dark matter and dark energy. It's fascinating to reflect on just how far astronomical observation has come. In the past, astronomers were limited to what they could see through optical telescopes, but today, we possess instruments capable of detecting the full spectrum of light, from X-rays to radio waves, giving us a far more comprehensive view of the cosmos. Landmark experiments, such as those conducted by the Cosmic Background Explorer, or COBE, satellite, and the Wilkinson Microwave Anisotropy Probe, also known as WMAP, have been instrumental in mapping the cosmic microwave background with incredible precision. The data from these projects has not only bolstered the Big Bang theory, but also reinforced the idea that quantum fluctuations were a critical component in shaping the universe. Every new measurement we take acts as another piece of the puzzle, helping us construct a more complete understanding of reality. Of course, some may question whether alternative explanations for these observations exist. While the Big Bang theory is supported by a wealth of evidence, science always leaves space for healthy skepticism.
Criticisms of the model often highlight its current inability to fully account for phenomena like dark matter and dark energy. Yet, every critique also serves as a catalyst for new lines of inquiry and potential breakthroughs, as science is a discipline in constant motion. As our technology advances and we collect more data, our perception of the universe is continually refined.
In essence, astronomical observations have provided us with a cosmic map that validates both the Big Bang theory and the critical role of quantum fluctuations. Every star, galaxy, and faint ripple in spacetime contributes to the grand narrative of our origins. As our exploration of the cosmos continues, we consistently find that each answer we uncover only leads to a new set of even more profound questions. So, as you continue to look up at the stars, remember that the universe still has countless stories waiting to be told. The Big Bang Theory has been the cornerstone of our cosmic origin story for many decades, but I find it fascinating to consider what happens when serious arguments are raised against it. This topic invites you to challenge what you hold to be established knowledge. The concept that everything emerged from a singularity, a point of unimaginable density and heat, is the widely accepted view. However, some researchers contend that this is not the only plausible explanation for the birth of the cosmos. For instance, one alternative proposed by some scientists is that the Big Bang was not a singular event, but rather one phase in an endless cycle of expansion and contraction. You can visualize this as a balloon that is perpetually inflating and deflating. In such a cyclic model, our universe expands following a Big Bang, eventually contracts into a Big Crunch, and is then reborn in another cosmic explosion. The thought that we might simply be living in one of many universal iterations is an intriguing one, isn't it? Another challenge to the standard Big Bang model zeroes in on the absence of conclusive proof regarding what transpired in that very first moment. Although the cosmic microwave background is considered a relic of the Big Bang, some scientists propose it could be interpreted in other ways. What if this ancient radiation is not an afterglow from the universe's dawn, but is instead the byproduct of an entirely different cosmic event we have yet to identify? It is crucial to maintain an open mind, as science is perpetually evolving. Furthermore, the standard cosmological model, which is built upon the observation of galaxies receding from one another, is also being questioned. Could there be alternative reasons for this galactic motion? A number of scientists theorize that gravity might operate differently on immense scales than our current understanding suggests, which would necessitate a new interpretation of galactic movement. It is as if you are observing a river that appears to flow in a single direction, when in fact its course is being shaped by powerful unseen currents beneath the surface. The Big Bang model also confronts significant challenges when you consider the puzzles of dark matter and dark energy. These concepts are currently essential for explaining the accelerated expansion of the cosmos. But what if they simply don't exist? It's possible we are observing a cosmic phenomenon that can be explained without resorting to these dark ideas, creating a rich environment for both scientific speculation and creative new theories. Science has a long tradition of favoring simplicity and searching for the most straightforward explanation for any given observation. However, many argue that the incredible complexity of our universe can't be traced back to a single initial event. The proposition that everything you see and experience is merely the outcome of one Big Bang could be far too simplistic, hinting that the universe is profoundly more intricate than we currently grasp. Quantum physics also joins this debate, suggesting a far different origin story. Imagine that instead of a neat and predictable beginning, the universe erupted from a state of pure quantum chaos. This theory posits that unpredictable quantum fluctuations might be the very key to understanding the cosmos's birth, a perspective that naturally opens the door to the concept of a multiverse, where every fluctuation gives rise to a distinct reality.
Challenging the Big Bang Theory is more than a simple intellectual exercise. It speaks to our deep-seated need for a more complete and holistic understanding of the universe. Although the Big Bang has served as a pillar of modern cosmology, science is a discipline that flourishes on doubt and the constant revision of its own ideas. By questioning its foundations, we venture into new frontiers in our comprehension of existence itself. The entire history of science is filled with examples of theories once held as absolute truths that were eventually overturned. The geocentric model, which positioned the Earth at the center of everything, was ultimately supplanted by the heliocentric view. In the same vein, criticism of the Big Bang can be seen as a logical progression in our ongoing quest for truth, as science often advances through the clash of competing ideas and theories. Ultimately, by examining the critiques of the Big Bang model, you are invited to ponder the very nature of knowledge itself. Could it be that by questioning what we accept as fact, we actually move closer to the truth? Every new question that arises carves out a new avenue for exploration and discovery, reminding us that science is not a final destination, but a perpetual journey toward deeper understanding. This search for the truth about the universe's origin stands as one of humanity's most profound undertakings. Alternative theories to the Big Bang are not just a compelling field of study. They serve as a powerful reminder that curiosity and skepticism are indispensable tools in our pursuit of knowledge. It is this very impulse to uncover the unknown that has consistently pushed humanity to explore the farthest reaches of the cosmos. So, when you encounter criticism of the Big Bang Theory, I believe you shouldn't view it as an assault on established science. Instead, see it as an invitation to dive deeper into the universe's great mysteries. Doubt, after all, is the very first step toward genuine understanding. And on this journey, each answer we find only gives birth to new questions, compelling us to look beyond the limits of our current knowledge. What if the universe never actually had a beginning at all? While this idea might sound peculiar, it is the central premise of the eternal inflation concept. Picture an ocean in a state of constant flux, where every wave is a bubble of space-time that is continuously expanding and forming. In this metaphor, each of these bubbles represents not just an individual universe, but the product of an infinite inflationary process that could be happening right now in some distant corner of reality. While we tend to focus on our single universe, the theory of eternal inflation proposes that there wasn't just one Big Bang that created everything we know. Instead, it suggests a continuous series of Big Bangs, each generating its own unique universe within a vast sea of infinite possibilities. This implies that we might be living inside one privileged bubble, while countless other bubble universes exist with entirely different laws of physics, each developing its own history, dimensions, and perhaps even its own forms of life. One of the reasons eternal inflation is so significant is that it helps account for some of the peculiar features of our own cosmos. For example, it offers an explanation for the remarkable uniformity of the cosmic microwave background, the relic radiation from the early universe, which shows that on the largest scales, everything is surprisingly homogeneous. Eternal inflation could be the reason that regions of space, despite being so far apart, appear so perfectly coordinated, as if each bubble was stretched and smoothed out. However, this concept also presents some truly fascinating questions that force you to reconsider your place in the cosmos. If there are an infinite number of universes, what makes ours special? It could be that we are simply a fortunate accident in an endless ocean of cosmic possibilities. This line of thought leads to profound reflections on existence itself, raising the possibility that in another universe, a different version of you might be living an entirely different life.
The idea of a multiverse can feel bewildering, especially when you ask how we could ever prove the existence of other universes we can't directly observe. But science often makes progress with theories that are difficult to test, and eternal inflation is a prime example of an idea that pushes the boundaries of our comprehension. Nevertheless, scientists are actively searching for methods to detect faint traces of these other universes, perhaps hidden in the cosmic background radiation or in the large-scale structure of the cosmos. To help you visualize this, imagine you are in a movie theater watching a film with what appears to be a single, clear storyline. Then suddenly, you realize that there are multiple potential endings to the story. In the context of eternal inflation, each of those possible endings represents a different bubble universe. That's a simple way to conceptualize the multiverse. Each bubble is a different outcome, a different story being told. Every universe tells its own unique story, and when you stop to think about it, the sheer number of narratives that could be unfolding at this very moment is staggering. This idea brings up some profound philosophical questions. For instance, if there is an infinite number of universes, does it follow that everything conceivable is actually happening somewhere? It's possible that in another universe, the physical laws are so different that life could evolve in ways you and I can't even begin to fathom, prompting us to reflect on our own existence and our place in the cosmos. As we explore the enigma of eternal inflation, it's crucial to acknowledge that many of these concepts remain in the theoretical stage for now. The scientific method is built upon a foundation of observation and hard evidence. While eternal inflation presents a compelling framework, a great deal more research and empirical data are required to truly substantiate it. As science advances precisely through the rigorous process of questioning and critiquing its own theories. So, you might wonder what this all signifies for the future of our cosmic understanding. Investigations into eternal inflation in the multiverse could unlock entirely new pathways for comprehending not only the genesis of our universe, but the fundamental fabric of reality itself. As scientists probe the frontiers beyond our known cosmos, we may find ourselves uncovering incredible connections and revelations that could completely reshape our perspective on what it means to exist. The quest for answers in this field is as much a philosophical odyssey as it is a scientific one. It compels you to re-examine your own identity, your collective history, and the destiny that lies ahead. Eternal inflation in the multiverse, that theoretical assembly of all conceivable universes, serve as a powerful reminder that while we may feel isolated in our cosmic bubble, we are part of something vast and often beyond our comprehension. Ultimately, the theory of eternal inflation provides an exhilarating and intricate vision of reality. It encourages you to imagine the possibility that our entire universe is merely one small piece of a far more magnificent whole. Although these concepts might seem abstract or far removed, they stand as a testament to our relentless human curiosity and our deep-seated desire to make sense of the cosmos around us. This exploration is not just a scientific pursuit, it's a journey into the very core of existence. Quantum fluctuations represent a captivating idea that has sparked the curiosity of both scientists and philosophers alike. But to truly grasp what they are, you need to journey into the strange world of quantum mechanics. Within this domain, subatomic particles are not the definite, predictable objects we know, but instead behave according to probabilities. This means a particle can be in many places at once, its final state remaining undecided until the moment you measure it. This probabilistic nature opens up the fascinating idea that in a vacuum, a space that seems utterly empty, there is actually a ceaseless ballet of particles popping into and out of existence. Picture, if you will, the surface of a perfectly still ocean. While it appears tranquil, a closer look reveals tiny ripples constantly forming and then disappearing. These fleeting waves are an excellent analogy for quantum fluctuations, where virtual particles emerge from the void, exist for an infinitesimal moment, and then vanish again. Yet their influence may be far greater than you'd think. So, what proof do we have that quantum fluctuations are real? The classic double-slit experiment offers compelling confirmation. When you shine light through two parallel slits, you observe an interference pattern, showing that light acts like a wave. However, the moment you try to measure which slit the light goes through, it behaves like a collection of individual particles. The fact that light can be both a wave and a particle is astonishing, and it suggests that the vacuum is not truly empty but is instead teeming with potential energy capable of creating matter. There's another remarkable experiment that provides evidence: the Casimir effect. This phenomenon occurs when you place two uncharged conductive plates extremely close to each other in a vacuum. You'll observe an attractive force pulling them together, as if something invisible were pushing them from the outside. This force is a direct consequence of the quantum fluctuations in the space between the plates, demonstrating that the vacuum is, in fact, a very dynamic environment filled with energy that can affect the world you see. But how do these minute fluctuations connect to the creation of matter in the infant universe? Imagine you're standing in a massive hall when the lights suddenly start to flicker erratically. In that instant, anything could happen. Similarly, in the primordial universe, moments after the Big Bang, quantum fluctuations may have been the very trigger that caused the first particles to crystallize from the vacuum, giving rise to all the matter that constitutes everything you know today. The formation of particles was just the beginning. Quantum fluctuations can initiate a whole cascade of processes that steer the universe's evolution, from the assembly of atoms to the formation of vast galaxies, and eventually planets like our own. So, the next time you gaze up at the night sky, you can appreciate that every star has an origin story that traces back to these minuscule ripples in the fabric of space-time. And what about the great cosmic mysteries of dark energy and dark matter? It's possible that these concepts, which are vital to our current model of the universe, are also tied to quantum fluctuations. The dark energy that appears to be accelerating cosmic expansion could very well be an expression of these vacuum fluctuations. Therefore, by studying them, you are not only investigating the universe's past, but also seeking to understand its ultimate fate. Their influence even extends into particle physics, where these ripples might be the underlying cause for phenomena like particle decay and the emergence of new particles in high-energy accelerators. Have you ever considered the staggering connection between events at the core of a particle accelerator and the very principles that govern the birth of our universe? As we delve deeper into the nature of quantum fluctuations, we are confronted with some profound questions. What is the true meaning behind the concept that a vacuum is not genuinely empty? Could these vacuums actually be oceans of infinite potential that we are only just beginning to comprehend? These inquiries extend beyond science into the realm of philosophy, compelling you to contemplate the fundamental nature of reality itself. In this way, quantum fluctuations serve as a powerful reminder that the universe is a far more intricate and awe-inspiring place than we can possibly conceive. Every time you gaze into the night sky, you are witnessing an echo of the distant past, a time defined by both chaos and creation. It is all thanks to these tiny, fleeting fluctuations that our reality has been sculpted into what it is today.
The theory that our entire universe could have sprung from a single quantum fluctuation is an undeniably mesmerizing idea. But what does this concept truly signify? And what are its consequences for how we perceive reality and our own existence? Let's investigate these questions together and ponder the deep philosophical ramifications that stem from this powerful notion. To begin, I want you to imagine the universe as an immense ocean, one filled with small waves that continuously form and vanish, even when the water appears perfectly calm. These waves represent quantum fluctuations, minuscule shifts in the energy of the vacuum that could, in theory, spark the creation of particles and, eventually, everything we can observe. If this is how the universe came to be, isn't it breathtaking to think that all you see, from the most distant stars to our own planet, might have originated from something so small and transient? From a philosophical standpoint, the idea that something can emerge from what we perceive as nothing forces us to ask deep questions about the very essence of being. What does the term nothing actually represent? If the quantum vacuum, which appears to be the most fundamental state of reality, can give rise to existence, what does that suggest about our long-held beliefs concerning creation? The possibility that the universe emerged from a quantum fluctuation fundamentally challenges many of our conventional origin stories and invites us to consider a cosmos where creation is an inherent quality of reality itself. Consider what it would mean if you were living in a cosmos where matter and life can arise naturally, flowing into existence as effortlessly as a river follows its course. If this were true, our lives might be the outcome of a grander cosmic process, with each of us being just one wave in this vast and dynamic ocean. The concept of quantum fluctuations also urges you to re-examine your perception of time. If, as certain interpretations of quantum mechanics propose, time is merely an illusion, what does that imply for your daily experience? It suggests that reality could be far more fluid and interconnected than we typically believe, with time and space interwoven in ways we have yet to grasp. Furthermore, the theory that the universe exists in a perpetual state of creation leads you to reflect on your own connection to the cosmos. If we are all the product of a quantum fluctuation, does that mean we share a fundamental link with everything else in existence? This sense of interconnectedness can be a profound source of both wonder and humility, reminding you that you are part of something immeasurably larger than yourself. This idea resonates with concepts in Eastern philosophy, such as the unity of all things, suggesting that if everything is interdependent, then every one of your actions may ripple throughout the cosmos. Thinking about this can fundamentally alter how you live your life and interact with others, inspiring a greater sense of compassion and mindfulness. At the same time, the notion that the universe can spring from nothingness also brings the principle of causality into question. If quantum fluctuations can generate particles and energy seemingly from scratch, perhaps causality is a far more intricate concept than we have assumed. It hints that there may be dimensions of reality that operate beyond the laws we currently believe to be absolute. Reflecting on these possibilities also has a significant impact on how you might understand life and death. If the universe is in a constant state of flux and creation, perhaps our own consciousness is an integral part of this dynamic process. It could be that life and death are not endpoints, but are instead two facets of the same phenomenon, a continuous cycle of transformation within an ever-evolving cosmos. This perspective can inspire a profound sense of awe, reminding you that there is so much more to reality than what is immediately apparent, and inviting you to remain curious and to never stop exploring.
Ultimately, the idea that our universe could have emerged from a simple quantum fluctuation leads us to a position of deep humility. It shows us that despite all our scientific progress and achievements, we are still surrounded by profound mysteries. This space of uncertainty, while potentially unsettling, is also the very ground from which new exploration and discovery can grow. As you contemplate these philosophical implications, remember that every question you ask is part of an unending human quest to comprehend our place in the universe. This journey, sparked by a single incredible idea, is just the beginning.
Among the most compelling cosmological ideas is the cyclic model, a framework that envisions a universe perpetually undergoing rebirth. You might wonder how this concept connects to the Big Bang and the quantum fluctuations we've discussed. To see the link, you have to grasp the model's core principle. A cosmos without a distinct start or finish, locked in an endless rhythm of expansion and contraction. Picture it as a cosmic lung, inhaling toward a single point and then exhaling outward in a new Big Bang, potentially birthing a completely new reality with its own set of physical laws. This vision naturally leads you to ask what could possibly drive such an immense and repetitive process. Scientists exploring this model often point to gravity as the primary mechanism. As the universe inflates and galaxies rush apart, their collective gravitational pull acts as a brake. It's theorized that this attraction could eventually become strong enough to halt cosmic expansion and pull everything back into a cataclysmic collapse, setting the stage for the next cycle. This is a fascinating idea, but it also carries the immense burden of finding supporting evidence. A significant hurdle for the cyclic model, however, is the concept of entropy. According to the second law of thermodynamics, disorder within a closed system can only increase over time. This implies that with each successive universal cycle, the cosmos would become more chaotic and degraded. You're then faced with a difficult question. How could the fundamental laws of physics remain stable if the universe reboots from an ever more disordered state? While some proposals suggest a rebalancing mechanism, it remains uncertain whether such a process could truly preserve cosmic continuity indefinitely. Another captivating theory that has gained traction is the idea of creation from nothing, which is deeply rooted in the science of quantum fluctuations. This concept suggests that our universe could have spontaneously emerged from the quantum vacuum, a void that is only empty on average. It's possible that these two frameworks, the cyclic universe and the one born from quantum uncertainty, are not mutually exclusive. They might simply be two different perspectives attempting to describe the same fundamental reality from alternate angles. Exploring this further takes you into the philosophical domain, where a cyclic universe challenges our very notions of time and existence. If the cosmos is caught in an infinite loop, what does that mean for our linear perception of time? Instead of a river flowing in one direction, perhaps time is more like a vast ocean of recurring possibilities, where everything that has been could be again. For some, this perspective offers a unique comfort, reframing the end of one life as merely the prelude to a new beginning. Of course, the cyclic model is not the only grand theory competing to explain cosmic origins. String theory, for instance, proposes a multiverse, a vast collection of coexisting universes, each governed by its own unique physical principles. You have to consider how this idea intersects with a repeating cosmos. It's conceivable that in a cyclic multiverse, every individual universe undergoes its own endless cycle of expansion and collapse, weaving an immense and intricate tapestry of interconnected realities. In this multi-layered context, the idea that each universe could be a product of quantum fluctuations becomes even more profound. If new universes can simply pop into existence from the quantum vacuum, then their creation might be a common, recurring phenomenon throughout the multiverse. This leads to a new and critical question. Could the cyclic model and the multiverse theory actually be complementary, with each one providing a vital piece of the puzzle that explains the origin and evolution of everything?
An entirely different approach, known as loop quantum cosmology, proposes that space and time are not continuous, but are made of discrete, indivisible units. This radical idea might offer a solution to the entropy problem that plagues the standard cyclic model. By quantizing space-time itself, could a balance be achieved that permits the cycles to repeat without descending into irreversible chaos? This remains a topic of intense debate among physicists, but it opens up exciting new avenues for research. Ultimately, comparing these diverse theories does more than just deepen our cosmic understanding. It reveals our own innate drive to find our place in the universe. Each model and every unresolved question inspires us to push the boundaries of knowledge even further. We're left to wonder what other secrets the cosmos holds within its limitless expanse. While we may never have all the answers, I believe the true marvel is found in the relentless pursuit of them. The search for cosmic origins highlights the nature of science itself. It's like assembling a giant puzzle where the pieces sometimes don't seem to fit, inviting us to keep searching for the complete picture. As our research progresses, new theories and discoveries will undoubtedly emerge, forcing us to reevaluate our current beliefs. The great mystery of the universe remains alive and well, and for every answer we find, a host of new questions arises, compelling us to ask what we truly know about our cosmic home. This forward momentum in cosmology is not just a journey into the unknown. It's an awakening of the deep curiosity that defines us as a species. What enigmas are still waiting to be uncovered in this vast ocean of stars and galaxies? Modern cosmology is in a constant state of evolution, with every technological breakthrough providing new windows through which to view the cosmos. Among the most promising fields is the study of dark energy, the mysterious force that appears to be accelerating the expansion of our universe, adding yet another profound question to our quest for understanding. The enigma of dark energy continues to captivate the scientific community, acting as an unseen current that drives the universe's accelerating expansion. Likewise, dark matter presents a profound puzzle, its gravitational influence shaping the structure of the cosmos, even though it remains completely invisible. Scientists are developing ever more sophisticated experiments to detect these elusive components, as each potential discovery promises to bring you closer to understanding how these invisible forces sculpted the galaxies we see today. The search for gravitational waves marks another revolutionary frontier in our comprehension of the universe, allowing you to listen to the echoes of colossal cosmic events like merging black holes. At the same time, the exploration of exoplanets, worlds orbiting distant stars, is rapidly gaining momentum, driven by the profound question of whether life exists elsewhere. Each new exoplanet discovered makes the prospect of other civilizations feel more tangible, fueling missions designed to scan their atmospheres for biological signatures. Artificial intelligence is emerging as a pivotal tool in cosmology, offering the ability to analyze vast data sets and uncover subtle patterns that would otherwise escape human observation. Alongside AI, complex computer simulations play a crucial role, allowing you to test theories by modeling the universe's evolution. As these digital models grow more sophisticated, they may finally reveal how initial quantum fluctuations blossomed into the large-scale cosmic structure you inhabit. International collaboration is an indispensable component of this quest, with projects like the James Webb Space Telescope uniting global talent to provide an unprecedented view of the early universe. Looking ahead, next-generation telescopes are poised to completely transform our perspective, enabling you to observe objects more distant and ancient than has ever been possible.
Every new piece of data gathered could hold the key to finally unlocking the mysteries of the universe's origins. This thrilling voyage of discovery confronts you with the most fundamental questions about our own existence and our place within this immense cosmos. Investigating the universe is not merely a scientific endeavor. It is a deep exploration into what it means to be human. Every answer we find seems to only generate new questions, fueling a perpetual and inspiring cycle of curiosity.
The intersection of science and philosophy becomes especially clear when you consider the idea that our entire universe could have arisen from a single quantum fluctuation. This is not just a technical question, but a profound inquiry into meaning itself, compelling you to reflect on your own nature and the part you play in this vast web of matter and energy. As we advance into the future, the boundaries of knowledge are constantly expanding, driven by innovations in technology that promise to elevate our understanding to a new level. The concepts that seem like science fiction today could very well become established fact tomorrow, as each discovery reminds you of how much remains to be learned. Human curiosity is the relentless engine driving this exploration forward, with the universe patiently awaiting your next question. Ultimately, the future of cosmology is filled with both exciting possibilities and unknown challenges, as we continue to seek an understanding of our origins. This incredible journey has only just begun, and you are an integral character in this unfolding cosmic narrative. The epic story of the Big Bang, where everything you see emerged from an infinitesimal point, forces you to confront the very nature of reality and ask whether the quantum vacuum is truly empty, or if it is a sea of potential waiting to become real. The story becomes even more captivating when you learn that this primordial explosion was likely triggered by quantum fluctuations, which in turn spawned the particles that would eventually form the stars and planets you see today. Quantum mechanics provides a glimpse into the bizarre and fascinating world of subatomic particles. Scientists have found that while this realm may appear chaotic on the surface, it is governed by an underlying order that continuously sparks our curiosity, making us ask what other secrets this microscopic world, so alien to our own, might conceal. The link between the quantum and the cosmic is absolutely fundamental to understanding not just how the universe began, but also how it continues to shape our reality every day. This leads us to the thrilling possibility of the multiverse, the notion that our universe could be just one among a vast collection of others. While the concept might be challenging to fully comprehend, it opens up a staggering diversity of possible realities, pushing the boundaries of what you might think is possible. Contemplating alternate universes, where the very laws of physics are different, can feel like a journey into science fiction. Yet it is a frontier that science is now seriously beginning to investigate. You have to wonder what consequences this could have for our perception of life and the cosmos itself. Even the quantum vacuum presents us with profound paradoxes. The idea that empty space, which you perceive as nothingness, is actually a churning brew of quantum activity, is simply mind-boggling. This forces you to reevaluate the very essence of existence and ask whether matter is the norm or merely an anomaly in the grand scheme of things. Quantum fluctuations are far more than a curious phenomenon confined to a laboratory. Their influence is cosmic in scale. It was infinitesimally small variations in the density of the early universe that seeded the formation of galaxies and the vast clusters they inhabit. Which begs the question of what other cosmic enigmas could be unraveled by studying them further. Moreover, concepts like string theory and symmetry breaking reveal a landscape of even greater complexity. While symmetry is a foundational principle in nature, the act of breaking it can give rise to entirely new physical realities.
Could it be that the very birth of our universe is fundamentally tied to a loss of perfect symmetry? Thinking about this challenges you to reconsider everything you thought you knew about order and chaos. The cosmic microwave background radiation, that faint afterglow of the Big Bang, serves as an invaluable artifact from the dawn of time. By analyzing this relic radiation, scientists can peer back into the conditions of the infant universe. You can't help but wonder what other remnants of that ancient past lie hidden, just waiting for us to find them. The quest for these answers represents one of the most incredible adventures in all of modern physics. As our investigations lead us deeper into the realms of dark matter and dark energy, you come to appreciate just how mysterious and enigmatic our universe truly is. These invisible components appear to dictate the structure of the cosmos, defying our current models of gravity and matter. This journey of discovery surely holds many more surprises for us, forcing us to constantly revise what we believe to be true. The journey through general relativity has taught us that space and time are inextricably woven together. This revolutionary theory has reshaped our view of the cosmos and has been validated by an overwhelming number of experiments. A key question remains: how do these concepts of malleable space and time relate to the creation and ongoing expansion of the universe? Naturally, the immense challenge of explaining the Big Bang has drawn its share of criticisms and spawned alternative models. Science is a process of constant refinement, with each new hypothesis adding another layer of depth to our cosmic picture. This makes you question whether we are on the verge of solving the ultimate mystery of creation, or if an even longer road of discovery lies ahead. The theory of eternal inflation, which proposes an ever-growing multiverse, suggests that the universe is not a static entity but a dynamic, ceaselessly changing tapestry, prompting you to contemplate your own place within this immense cosmic ocean. Ultimately, as you look toward the future, cosmology stands out as a field brimming with vitality and potential. New technologies and innovative thinking promise to illuminate the puzzles that still confound us. But with each answer we find, a cascade of new questions seems to arise. Exploring the universe's origins and the nature of quantum reality doesn't just deepen your understanding of the world around you. It invites you to reflect on the very nature of your own existence. This is where science and philosophy merge, reminding us that while the universe may have had a strange beginning, our drive to comprehend it is what makes us truly extraordinary.